Hey, hi everybody, welcome back to the channel. So Google has come out with some big news regarding their quantum computer. They've come out with an article called Suppressing Quantum Errors by Scaling a Surface Code Logical Qubit. So this is claimed to be quite a big breakthrough. It's been on the cover of many different outlets, as you can see here. They also have this fancy video, shot very artistically in the darkness of their labs.
What's going on? Has this happened before?
But there's actually been several other papers that have come out in the last few years also talking about quantum error correction. For example, there's this one from 2021 which is talking about using ion traps to make a 13-qubit Bacon-Shaw code. There's another paper that's come out last year, which is using actually NV centers, diamonds, and they also made a fault-tolerant circuit with 7 qubits. And there's even been one with superconducting qubits and using a surface code. It's a little bit smaller than the one that Google came out. So there has been some works that have come out in the last few years. So the question is, so what is the actual breakthrough that Google has done this time? And so we're going to basically take you through the paper. Okay, so before we get into the actual paper, we need to have a little bit of basic knowledge of quantum error correction. So let's just talk about that for just a couple of minutes. Okay. So firstly, what is the aim of quantum error correction? So obviously it is to correct errors. So for example, if you've got a qubit on the left here, that's your qubit that you want to protect. And if an error happens on it, then qubit is now corrupted, right? So this is what you want to kind of prevent. And so the simplest way to kind of prevent this is to use some kind of duplication, right? So instead of encoding the qubit using just a 0 and a 1, you encode it with 3 zeros and 3 ones, for example, here. So if now an error happens, say, on the first qubit, then as you can see, you can actually tell that an error has happened because obviously, the odd man out here, for example, in the first one here, 100, you can tell that basically the error has happened on the first qubit. And that means that we can actually figure out what needs to be done to correct it. And the way that we actually figure out what qubit the error has happened on is using these so-called syndrome measurements. And in the case of the bit flip code, you measure these things, observables like Z1, Z2, Z2, Z3, Z1, Z3. And if no error has happened, then these should all be basically 1, right? But if an error has happened, then one or more of these flip, and then you can figure out where the error has happened.
Is this a common way to duplicate the qubits and then check the error correction?
Right, yeah. So this is called the bit flip code, the one that I'm talking about right here. And this was basically one of the first error correcting codes. Actually, Peter Shaw was the one that actually, I think, thought of this. In fact, he was the one that basically worked out the first 9 qubit codes.
You're dead. You crazy son of a bitch, you're dead.
So 9 qubits making one logical qubit, and then people started to improve upon the whole kind of thing with various different tricks. And these days there are much more modern codes, but conceptually this is basically what actually any error correcting code is always doing, right? So going back to our example here, so if you figure out that the error has happened on the first qubit, then basically all you have to do to correct it is to apply another X gate on the first qubit, and then you're back to where you started. And so this completes the quantum error correction cycle. Okay, so this is basically the kind of thing that we want to do. Now, the important thing here is that there are these operators that we just saw a few moments ago, and these are called, in this context, stabilizers, right? And they're called stabilizers because the key property that these operators have is that you apply it to the states. Yeah, and basically, it doesn't change the state, right? So you can apply these measurements as many times as you want, and basically it's not going to change the state. And so what you can do in this situation is that, you can keep on checking whether the state has had an error on it or not, right? So you just go and say, okay, has an error happened? Okay, no, good. Okay, error happened, no, good, no, good. And then, but at some point, an error will happen, and then you will realize, oh, errors happened. Okay, now we can go and do something about it, right? Okay, so now let's go to basically what the Google paper has actually done. Okay, so this is like figure 1 in their paper. So what you see here is the arrangement of qubits. And so you have a bunch of yellow qubits here and a bunch of blue qubits. So let's first start off by looking at the yellow qubits, which is really the important qubits, which is storing the information. So if you look at just the yellow qubits, what they use is a so-called surface code in order to basically encode a logical qubit. So eventually this thing is actually just encoding like 1 qubit. The special property that these surface codes have is that you can apply these plaquettes, so these squares of operators to the state, and the state doesn't change. Just like the Z operators that I showed for that simpler example before. In fact, the bit flip code that I showed is actually some limiting case of this surface code even. The difference to the bit flip code is that this thing can actually encode a full qubit, whereas actually the bit flip code can only correct for bit flips. And if there's a phase flip, it doesn't work. But this one can fully correct all kinds of errors, at least for there's 1 qubit. The Z's are oriented in this way, so it's sort of like every other plaquettes is a Z square, and then the alternating ones, the X's, the dark blue ones here, and so if you apply X's in those positions...
So no 2 Z come together, I think, diagonally or...
Right, it's always 4 Z's, actually. But there's one exception which you might be thinking of, which is actually on the edges, there are actually some places where it's just 2 Z's. But generally, in the middle of the lattice, it's always 4 Z's or 4 X's. Okay? That's basically the kind of state that we're making on the yellow qubits. Okay? So then what are these blue qubits? Well, basically, in order to make that measurement of the 4 Z's or the 4 X's, you basically need an ancilla qubit in order to do it, right? Okay. Basically, there's a little circuit that you can do, which is just on the right here, and the blue one is basically the ancilla or the extra qubit, and then the other 4 are the 4 real qubits arranged in a square. Yeah. So you do that circuit there for all these different squares. Well, actually, sorry, this one is for the 4 Z's, which is the light blue ones. For the 4 X's, there's a slightly different circuit that you do, but the story is still basically the same. So in the middle of each square that you see in the yellow qubits, there's a qubit there which is purely performed there to do basically just the measurements of either the 4 Z's or the 4 X's. Okay. And the gray ones they don't use. The actual surface code that they use kind of 2 different varieties. So the 5x5 grid, the yellow ones, that's basically one configuration that they use. And so there are 25 qubits that are actually encoding the actual state. And then there's 24, which are all the blue qubits. If you count them up, there'll be 24. Those are used for the measurements. And then, so Manish, the thing that you mentioned for the 2 Z's, so those things that are sticking out on the sides there, those are actually measurements to do with, like, say, 2 Z's, right? Or 2 X's. And all this encodes just like 1 logical qubit. And the way that you can actually read out the logical information is that actually you do either an X measurement or a Z measurement. And so the green line that you see on the bottom there, if you measure in the X basis, all those 5 there, multiply them all together, then that will be actually your X readout. So your logical measurement is actually just that. And this is something that we also saw in the ordinary bit flip code. For example, if you wanted to know what the logical X of this encoded state is, what you'd do is you'd actually calculate the expectation value of XXX. Right? And then that actually gives you the X readout. In this case, the Z logical is just any one of those Z's. And they compare it to like a smaller surface code. And so they have a smaller patch of this surface code that actually makes up like a 3x3 surface code. So there's 9 surface code qubits. You need 8 ancilla qubits in order to do the measurement. And then that again makes 1 logical qubit. The logical X operation would be a string of 3 X's in this case. That's basically the setup. And so what do they actually do in the experiment? Well, what they do is they first start off by preparing the surface code. And they do this basically by first initializing a bunch of qubits, which are in the Z basis. And then they keep on applying either the 4 X's or the 4 Z's. And they do that by doing that circuit, which I showed. So basically that's continually projecting it into this same surface code state. So ideally, if you do that, in a world with no errors, you'll just keep on getting some particular readouts, right? For each of those 4 plaquettes, each one of those gives one measurement. And so the blue and light blue checkerboard, that is, for example, like the ideal readout of the surface code, right? Now, from there, say an error happens. On the first one that they show here in the red is actually an error happening on like one of the yellow qubits, okay? Then, they're continually doing that circuit with the, 4 C0 gates. Then what happens, because you have these C0 gates, the error due to that initial Z error actually kind of spreads out. And so that error is seen on potentially 2 syndromes. So the 2 red outputs there that you see at t = 0 here are like 2 errors that will happen because you can trace it back to a Z error happening on one of the yellow qubits. Right? The purple one here is a case, for example, where an error happens on one of the blue qubits. That's one of the measurement qubits. And then in this case, you get a so-called time-like pair, which basically means that there'll be some change in the syndrome from one time step to the next time step, right? So you can see the purple one is changing from 1 to 0, and so that's the kind of signature of that type of error. The blue one is if an X error happens somewhere between, in the middle of that quantum circuit when you're doing that measurement, and then in that case you get like an error that changes the syndromes. It's separated in space in terms of the pattern, but also between 2 steps in time. So different types of errors have like different signatures. And then finally, they go and measure the whole bunch of qubits, either in the Z or the X basis. And then from that, they can kind of infer something about the logical state of the whole thing. Okay, so what do they actually see in the actual experiment? So firstly, these graphs are basically just detecting, what probability are they actually detecting an error, right? So basically, anytime you're doing all these measurements constantly, measure. Ideally, it does not change between different cycles, right? But then occasionally it will. And then so basically, what is the probability of any one of those syndromes changing between like one time step to the next time step, right? And then so the probability they get is something like 0.18. So basically, roughly 1 in 5, or 1 in 5 or 6 cycles, you'll see some error happening somewhere, right? Okay, and then so the one on the left here, you're seeing this is for that full like 5 by 5 surface code. They repeat the experiment with like 4 smaller patches, like 3 by 3s, and then what they find is that it's basically roughly the same number, I guess, because it's the same physical system. If you're wondering what that weight 4, weight 2 stuff is, the weight 2 is the thing on the edges, the thing that you were talking about. Yeah. So those always have a lower probability because they only involve like two qubits. Okay, so now coming to the main results of the paper that they really want to show. Eventually, what we want to do in this whole error correcting situation or round is that an error happens, you detect it, and then you correct it. And then you have some final state, which is the final logical state. And ideally, the final logical state is the same as the initial logical state, right? So, you want to compare the sort of the input to the output and basically make sure that it's the same. Okay. So firstly, actually, they don't actually literally do this X correction. They don't actually apply like another gate in order to make that final X correction. And I think that's because basically you can always account for this just by some post-processing, right? So I don't think they literally need to actually account for it. But actually, what's more, it's not quite as simple as what you think, because what you would think is that, okay, so you start with the state and then you measure the final state and then you compare the two and, you just see how different they are, right? So, do some kind of fidelity. But it's actually not what they do. And if you read the paper carefully, and this is from the supplementary information, they say something like this, that however, there are many sets of errors which trigger the same set of detectors. So that basically means that when they detect errors, they can't exactly pin down exactly what error it was. So remember that whole story with different errors making different patterns. Apparently, this is still not sufficient to actually figure out exactly what happened, because if they knew exactly what happened, then they could go and correct it. But apparently, there's insufficient information. So what they actually do is some kind of maximum likelihood estimate of, given a particular error detection result, what is the most likely thing that happened, and then make their correction based on that. And then what they do is they, from there, basically estimate what is the actual probability of a logical error actually happening. So what they do is actually a little bit more complicated. It's not quite as straightforward as you would like, because you would like straightforward comparison of input, output, compare it. Okay, so how good is this thing actually working? Anyway, so that's what they do. So in the vertical axis, what they show here is the logical error probabilities, and horizontal axis is the number of cycles. So these are all the number of times that they're doing the full set of measurements. And what they basically are seeing is that as you do more cycles, obviously this is cumulative, right? So it's the same system and you keep on applying the measurements. And so if there's an error that occurred in the first step, then after more cycles, there could be another one and another one and another one. And so the probability of getting some kind of error, of course, increases. Okay. But the key point in this first one is that if you look at the line for the smaller code, so the d equals 3, that's the 3x3 surface code, it's actually higher than the probability for the larger surface code. So this is kind of the result that they were trying to show, because what should be happening is that overall there should be a benefit of using the larger code. In the larger code, yes, of course, there's more opportunities for errors coming into it because there's more qubits, but then overall there should be a net gain, and this is the whole idea of fault tolerance and stuff. So as you increase the size of the system, you should be benefiting, right, by doing so. And so this is basically one of the key results that they're showing. The bottom one is basically just kind of fitting this same thing to an exponential, but then looking at the probability of getting an error per cycle. The gradient here is, so the 3.28% that you're seeing there is saying that, okay, so per cycle, there's a probability of 3% of getting an error, logical error. Compare that with the larger one, which is the d equals 5. I think that should say epsilon 5, right?
Yeah.
I think it must be, right? Yeah, so I think the epsilon 5 must be for the larger surface code. So that has a slightly lower error probability per cycle, right? Per cycle, so each time. So so this is sort of the money shot result that they want to kind of show. They also showed like the experimental progress actually in order to get to this point where the 3x3 surface code is not as good as the 5x5. In all their previous experiments, the 3x3 was always better than the 5x5, but with various improvements, the 5x5 has finally overtaken the 3x3. And so I guess what this is supposed to imply is that, as they
qubits.
Yeah, as they develop their technology more, the 5x5 will definitely become better, but this is the first time that this has overcome that comparison. Finally, this is they also do actually just the regular bit flip code, and they do this kind of snake kind of configuration using, I think, 25 qubits. It'd be like a bit flip code where instead of 3 qubits, it's like 25 qubits, right? And what they show is that basically this logical error per cycle, the same quantity that we were calculating there, is actually dropping down to very, very low levels as you go to very large code sizes. They have some other results, but I think these are the main things. So what do you guys think? Are you impressed?
I was checking that plot where they compare
Yeah.
D3 and D5. So in terms of, I think, numerical values, how much is the improvement? Like how much % from D3 to D5?
Well,
very small.
it's pretty small. Yeah, it's pretty small. It's just a couple of %, right? I mean, in the error per cycle, it's 0.1%. So it's pretty marginal.
Yeah.
But I guess it's the first time that it's...
Larger surface code are used.
Yeah, the larger surface code beats the small surface code.
Because if we do the scaling for larger qubit, and they say 7 by 7 may further improve over 5 by 5.
You would hope so.
Yeah.
You would hope so, right? Yeah.
So, but overall, I think my question would be, what is the benefit of this error correction if, well, let me step back. Is there any hope of actually knowing the source of the error and correcting it as the system scales larger? Is there any hope of doing that?
Well, yeah, I don't know. I was a bit surprised, I guess, that in this probability estimate that they basically still can't really pin down actually what the error is, right? So the whole point of, I thought, error correction is that you can pin down where the error has, and then you can go and correct it, right? But if you can't, then I guess you need something more sophisticated. I mean, maybe tailored to the system that you're doing, because I guess the thing with this is that in my simplified example with the bit flip code, right, you're just looking at those qubits involving the yellow qubits in this example, right? You don't even talk about like how do you actually go and measure it. But I guess what this is saying is that, yeah, the measurements themselves can contain errors, and so the errors can come from many different sources in reality.
They use gates for the measurement that can introduce errors.
Yes. That basically comes to that. Yes.
Gates,
Is it that we should start thinking of better error correcting, would I call it, no longer codes, because codes already exist, but what is the best strategy to deal with the error in this case? I think that's what I'm trying to really get at. Because not naturally, I would think that if you told me there is no error or that the error is minimal, I would just simply look at the fidelity, right? But they're doing some, likelihood and blah, blah, blah. And so what is the best strategy now to track error in quantum systems? Because this is showing that maybe we are still far away from actually knowing or correcting errors, actually.
Yeah. Well, maybe the thing here is that because the actual measurement that you need to do is quite complicated, right? This, ZZZZ or, XXXX it's a pretty complicated thing that you need to actually measure. And because of that overhead, that introduces opportunity for more errors, right? So I guess ideally you have a relatively simple measurement that, still does it. But, I guess people have investigated quantum error correcting codes for a long time. And apparently there is no real simple way to do it. It's always something a bit complicated like this. I mean, surface codes are basically supposed to be the best.
Yeah.
It's supposed to be the best there is, right? All right, so you don't seem very impressed.
I don't know. I don't know. Even this idea that, if you scale, the larger you scale, the better, you're going to beat the small size thing. Okay. But if scaling bigger means more measurements and things like that, then so here they're using 25, right?
Yep.
So assuming they're able to scale it to maybe 50 or 100, what would be the performance of that compared to even just 3 or they should? Are they telling me that it will be better or is it going to be worse? So, from what they're saying, it should be better.
Well, but, if you just had one qubit, right? The gate, fidelities and stuff are like, 99.99 something, right? So I think at this point, like if you're actually doing some calculation,
Yeah.
it's actually better just to have one qubit for one logical qubit, right? One physical qubit for one logical qubit. But I guess the idea is that there is some point where it starts to really overtake. I mean, in this experimental graph, they've just crossed this threshold. So maybe as they further improve their technology, then they get deeper into this region where there's a lot more benefit for having the larger surface code. And then once you're into there, then basically it's just always a winning game to make larger and larger
surface,
surface codes, right?
So in future it might happen the 7x7 code might beat 5x5.
I suppose so, yeah. I mean,
but still it has larger number of measurements.
anything else? All right, we'll leave it at that. All right, so thanks for watching. See you for the next video.